Okay, next we're going to start the VPN section. We're going to take a look at the cryptography to begin with. Then we're going to take a look at the public key infrastructure, move on to IPsec VPNs, the fundamentals, and then the configuration of a site-to-site by IPsec VPN, and then SSL VPN, both client-based and clientless. So cryptography is going to apply to all kinds of VPNs back and forth, and it's important to understand the concepts like what does cryptography do, what are the different types of algorithms, and why would you use one type of algorithm over another, and what is the scope of each of those algorithms back and forth. Of course, it's a very complex technology, and just reading about it in one book in the CCNA official guide or watching the video is not going to be enough. But it is going to be, let's say, good enough to have just a fundamental understanding of what it's supposed to achieve, how does it work, and in which cases would you use one algorithm over another to let's say, to end up with, based on what you want to achieve, you're going to end up choosing different algorithms back and forth. So to begin with, let's speak about cryptography, like the overview. So what is cryptography? Is going to be methods or techniques, or methods and techniques used to secure communications in the presence of third parties, which means potential adversaries. So cryptography is used to secure, to call it simple, IP data, both in transit and at rest, which means as traffic travels, for example, looking at our diagram, so we would want, for example, let's say that this is going to be one part of our network in here, facing that direction, one site, and this is going to be another site facing that direction. So it means that router 3 in the middle is going to be a transit device, which is not trusted. It doesn't belong to our enterprise. So it means as traffic flows through router 3 from left to right, or from right to left, doesn't matter. So if traffic flows through router 3 between our company sites, I want to secure data in transit. This means in transit. I want to make sure that data cannot be modified or read in transit and altered by anyone in the transit network, which can be internet, a private line, or an MPLS, or doesn't matter. So that's going to be securing the data in transit. Or at rest, what that means is that as traffic, as for example, router 4 is going to, let's say, copy some files over to test server A. So as the files are going to be stored on the disk of the server or on a storage, doesn't matter where, you might want to also secure data as it's being stored on that server or on that storage in there. That's going to be data at rest. So you want to avoid any unauthorized modification to the data or any kind of unauthorized reading of the data, both in transit and at rest. In modern cryptography, goal is to provide that kind of security through confidentiality, which, as you're going to see, that's going to mean mainly encryption and decryption, through data integrity, which is going to mean to make sure that traffic is not being modified either in transit or at rest unauthorized. Like, you wouldn't want somebody to, as you send traffic from point A to point B between your sites, somebody in the transit network to just modify the data transparently without you being aware of that. Or at rest, somebody, like you have, let's say, your usernames and passwords stored in the database, you wouldn't want somebody to go in that database, which is unauthorized, and just read the passwords in clear text and modify them as they please. Origin authentication is going to mean that we want to make sure that traffic is being received from the right person, and non-repudiation. We'll also speak in a couple in minutes about what that means. So that confidentiality is going to mean encryption, which means we're going to somehow change the data not to be readable in transit or at rest. So like you would want, as traffic flows through that untrusted network, as I said in here, if what you send to that transit network is going to be a, I don't know, a PDF file, which contains, doesn't matter, let's say a single word or an image. Let's say contains an image. As traffic transits through the untrusted network, or as traffic is stored on that storage in there, you don't want to store that PDF file, that image, in clear text. So you don't want somebody in the transit network in here, which is unauthorized, to see the clear text data, or somebody who gets access to the storage in there to be able to see in clear text that PDF file, that image. You're gonna do some changes to the file, to the packet, so that in transit or at rest is not visible in clear text. That's gonna be achieved through confidentiality or encryption. Data integrity, as you stated, you got to make sure that traffic or data, like a transit packet being in transit or data at rest, cannot be changed unauthorized. That's going to be achieved depending on the use case, through hashing or through a digital signature, to make sure that packet was being received, or the file was being received from the proper source and not modified in transit. And origin authentication would mean that you would want to make sure that you receive the packet from the proper source, which means likewise this is going to be achieved through what is known as hashing, or as through a digital certificate. So origin authentication would mean, looking back at the diagram and to those two sides of ours, left and right, as let's say traffic is being sent left to right from router 4. So origin authentication, if traffic is being sent from router 4 with a source IP of, let's say, X, and is destined to server A to a destination IP of Y. So as this traffic is being sent to that untrusted network, when server A receives the traffic, server A would want to make sure that the packet was actually sent by the real source of X, which means router 4. Because of course somebody could, from the untrusted network in here, could of course inject a packet, route it in the network, and spoof the source of X, and of course send it to the destination of Y. So the receiver, the destination, has to make sure that needs a way to make sure that that data, the packet or the file, was actually sent by the real originator and was not spoofed in transit or at rest in there. That's going to be providing data origin authentication. We got to make sure that who the sender seems to be, it is actually the real sender that sent that traffic, and not somebody that spoofed the identity of the sender in there. And non-repudiation is going to mean it's going to be achieved through digital signature only, which the scope of non-repudiation, as the name implies, is we got to make sure that somebody cannot decline to have sent a message to begin with. So non-repudiation, when we implement to cryptography, non-repudiation, it means we're gonna make sure that the sender of a message cannot deny having sent the message. And this is usually provided to digital signatures. Like for example, if we're gonna speak in more details in digital signatures, one use case would be like one real use case. It's like your passport. It's like if you go and you go to your government to issue you a passport, they're gonna digitally sign the passport in there, and they cannot decline. They have not issued that passport to begin with. That's one kind of digital signature. Or in the computer world, it means that when we send the file from point A to point B, we're going to sign it, and somehow we're going to speak in more details when we go to the PKI infrastructure overview. We're going to sign that document inside. We're going to somehow sign the document so that the sender cannot decline to not have sent the document to begin with. Also, digital signatures is being used in internet banking. For example, it depends on, of course, the implementation of the use case of the implementation. Like when you go on your, online banking system, and you try to, let's say, spend some money, buy something from your account, or for example, make a transaction from your account to a friend's account. The first step you're going to do is you're going to authenticate yourself to get access in your banking account, and then in most cases you're going to be forced by the banking system to authorize a transaction. So that's going to be again some kind of pseudo digital signature, so that you cannot decline that you have not performed that transaction, because you were asked by the bank to, put some codes in there and to actually somehow pseudo sign a transaction, so that in order to confirm that you're actually the let's say, the person who actually does a transaction is not like a bot, a computer bot, which got access to your account, and it starts sending money back and forth between your account to other people's accounts. So non-repudiation again means that we need a way to make sure that a sender of a message cannot decline not having sent the message to begin with. So those are the main goals of cryptography, and then I'm going to speak about, of course, all options, all the possible algorithms, and which ones are going to be used for which of those four scopes, the four goals. So first of all, let's look at hashing overview. So hashing is going to be a one-way mathematical function. So pretty much all of those goals, cryptography, encryption, confidentiality via encryption, data integrity via hashing, non-repudiation via digital signature, origin authentication via hashing or digital signature, all of those are going to be in the end provided via mathematical algorithms. Of course, different algorithms in order to provide those each of those security levels that you would want to provide to an IP traffic. So hashing is going to make use of one-way mathematical function to provide data integrity and authenticity. So hashing is going to provide, depends of course on where do you use hashing function. It may provide data integrity, so it's going to ensure that data was not modified, unauthorized, in transit, or at rest. And data authenticity means it's going to also authenticate, is going to confirm that the message was sent by the real sender, not by a spoofed sender by a malicious attacker. So how hashing works, because it's one-way function, it means that data of arbitrary length serves as the input to the algorithm, and the output is going to be a fixed length hash, also known as a digest. And commonly used hash algorithms are going to be MD5, which stands for Message Digest 5 algorithm, and the hash size is going to be 128-bit. SHA-1, which stands for Secure Hash Algorithm version 1, which has a fixed hash length of 160-bit. And SHA-2, which means Secure Hash Algorithm 2 version 2, where the hash can be 224-bit, 256-bit, 384-bit, or 512-bit in size. So again, what's going to happen is we're going to see in a couple that when you do hashing, you're going to take a block of data, doesn't matter how big the data is, and you're going to put that data into the hash function, and regardless of the input, the data size, you're going to always end up with a fixed hash size, depending on which algorithm you're going to use, with a fixed hash size of 128-bit or 160-bit or whatever value, depending if you use SHA-2 version 2. Now, because it's a one-way function, technically speaking, the algorithm is irreversible. So what this means, it's a well-known, let's say, comparison with the orange juice. So like if you take the oranges as the input and the blender as the MD5 as the hashing algorithm. So as opposed to data being the input, you take oranges as the input and you put oranges in the hashing algorithm, which is the blender. And the result is going to be the orange juice, which in our case, in the computer world, is going to be the hash, the fixed length hash. And you cannot make the orange back from the orange juice. So that's why they call the hashing functions to be a one-way mathematical function. You have an input, which is the data, the block of data, that doesn't matter the size. You have an algorithm, you put the data in that algorithm, and you end up always, doesn't matter the size of the input, you always end up with a fixed hash size depending on which algorithm you're going to use. And you cannot from given taken if you have access to the hash, from the hash you cannot make back the data. That's why it's a one-way mathematical function. So when you end up with the orange juice, you cannot make back from the orange juice the orange itself. Now practically, okay, even though the algorithm is irreversible, it is still susceptible to attacks. It's going to be inversion attacks or collision attacks, two types of attacks. The most common attacks against hashing algorithms are known as collision attacks, which means that multiple inputs can produce the same output in there. So like for example, and this is going to make sense if you look in here at Wikipedia. So the hash function means, let's look at the image in here. So as you see in here, we have on the left side the input, which is arbitrary length of data. In my case, data being just, you know, names: John Smith, Lisa Smith, Sam Doe, and Sandra D. So that's the input, and each of those inputs is going to be and is going to enter the hash algorithm, which can be MD5, SHA-1, or SHA-2. And the outcome is going to be a fixed hash length depending on the algorithm being used. But clearly, because imagine like in a computer world, you're going to take a packet size 1500 bytes. You're going to put that packet inside the MD5 hash engine, and you're going to end up with a hash value of 128-bit. So you're trying to somehow identify a packet size 1500 bytes with a hash value of 128-bit. So clearly there are chances, collision chances, which means multiple packets of different sizes can unfortunately end up with the same hash length, because it's not a one-to-one mapping between the input size, which is 1500 bytes, and the output size, which is 128-bit, clearly. So for that reason, it can happen that multiple inputs can produce the same output when they are being parsed to the hashing algorithm. Like in here, that's what they're trying to explain in here, that if you take as the input Lisa Smith and you put that input inside the inside the algorithm, hashing algorithm, the output is going to be a fixed size hash with a value of 0, 1. If you take Sam Doe as the input, it's clear it's a different packet size. You put that packet inside the hashing algorithm, and you end up with again a fixed hash value with a value of 0, 4. So the size is fixed, but of course the data, the hash result is different. But the hash size is fixed, is going to be, like in the case of MD5, is going to be a 128-bit hash value. But of course, and what they're showing in here is that if you take the input to be John Smith and Sandra D, which is a different input, are different inputs, different sizes. Unfortunately, when you put those inputs in the MD5 in the hashing engine, MD5 or SHA-1 or SHA-2, they unfortunately can end up with the same output. So the same hash value as the output. That's called a collision attack. Now, of course, as you can imagine, the security strength, so that's one weakness of the hashing algorithm, that multiple inputs can produce the same output. And that makes sense, as I stated, because you try to reproduce to represent like a big packet size 1500 bytes or even bigger with a very small hash value, which is 128-bit, or which SHA-2 can be 512 bits. So for that reason, clearly the strength of the hashing function it has to do with both the strength of the algorithm. Clearly, SHA-2 is going to be a better, more secure algorithm because they fix some, design flaws or any kind of flaws that initially MD5 had, for example. And of course, the hash length. So clearly, the larger the hash value or hash size, which the maximum available size nowadays can be 512 bits. If you use SHA-2, it means it's more resistant against those kind of attacks, which means the collision attacks. Because the larger the hash value being resulted, it means that you're better off to match the actual size of the input, basically. So like ideally there's going to be no collision, close to no collision, if the input is going to be like, let's say, 500 bytes. You put that value, if you put that data in the hashing engine, and the output is going to be the same size, but of course not the data, just a random data in there is to be like a fingerprint or hash. But the hash is going to, if the hash would be the same size, then clearly there's going to be no way that like two inputs are going to end up with the same output. But we use small size values for the hashing algorithm, hashing function, because this hash value is going to be appended to the data packet. So it means that if the hash value would be too big, then we're going to have problems with fragmentation. We're going to have basically a lot of too much overhead in transit, and it's not worth it. So you have to make some kind of compromises in there. We want security, but we don't want too much overhead. So that's why we have nowadays bigger, we have algorithms that have bigger hash size values like SHA-2, which can be 512 bit, but it's not like as big as the input, which can be even 9,000 bytes or a jumbo frame of whatever size. Okay. Now the problem with the hashing algorithm, and I think I forgot to show you something in there, but it was actually, let's say, obvious. So with regular hashing, the input is going to be your data. So your data is going to serve as the input. The hash function serves as the algorithm, and the output is going to be the hash itself. So you take data as the input, you put it in the hash function, and then you end up with a fixed hash size, whatever the input size was to begin with.